So have you understood the S parameters right now? So the S parameters are basically applied at high frequencies. And of course, since it can also be related to the transmission lines, so you can define even for the voltage currents, but the main actual application lies in the microwave range. Okay. So first, let us discuss some problems on that, so then you can understand it better before going to Smith chart. So first, this question anyhow, you can see that and tell me the answer. What is the value? This is the question related to the impedance matching. So there is a transmission line of 225 ohms line is terminated to 256 ohms. So what should be the lambda by 4 line characteristic impedance in order to match these two? So reply, what is the answer? So Z0 prime is equal to root over 225 into 256. Yeah. You are going to get 15 into 16. So that will be 240 ohms. Okay, anyhow, we'll see the S parameter problems right now. So find the S matrix for the following network. So see the first one. So this is your main transmission line and this is your two-port network. So the two-port network consists of a 50 ohm resistor. Okay, this is your port 1 and this is your port 2. Now, subjected to this one, you have to define what is the S matrix. Okay, so let me define, let me do it for the first one and you are supposed to do it for the second one. Okay, when you see the first one, so let me write the equations. So what is B1 and B2 you are having? S11 into A1 plus S12 into A2. And B2 is equal to S21 A1 plus S22 into A2. So this is your 50 ohms line right now. Okay, and this is your 50 ohms and this is your 50 ohms. So let me call it as this is a port 1 and port 2. So listen here, this is very important. So suppose if I want to find out the value of S11, the S11 value will be equal to B1 by A1 provided your A2 will be equal to 0. Okay, so let me represent like this. This is my A1 and this is my B1 at port 1. And A2 is something like this and this is your B2. First here, you can see here actually I have not connected any source at port 1 and port 2. Right? As of now, there is no input at port 1 and port 2. In that case, if you see here, if suppose some energy is getting transmitted from here, A1, and when you are measuring the S11, your A2 has to be equal to 0. Physically, I have not connected any voltage or current at the second port. I have applied only the voltage at the input port. In that case, when your value of A2 will be equal to 0? Can you tell me? When you don't apply any input at second port, you have applied only the input at port 1, and in that case you should get the value of A2 will be equal to 0. Open circuit. No. See here, when you look at from this particular side, okay, you can see that A2 is something, the reflection from port 2. When you look from the port 1 side, so always just assume that you are looking from the port 1 side, your A2 is something looking like the reflection from port 2. Agree or not? Will you agree with me? When you look from the port 1 side, forget about port 2 is existing or not. You don't look into that side. So you try to bend your head and look it from the port 1 aspect. So when you are looking from the port 1 to port 2, your A2 is something like there will be a load connected at second port, and because of that some reflection is coming back. Will you agree with me? Now what will happen? If you assume that A2 is the reflection from port 2 and it has to be equated to 0. So which means your reflection will become 0 provided if there is a load impedance of 50 ohms. Agree? Is my assumption correct? In order to make the value of A2 is equal to 0, I have to terminate the second port with a 50 ohms. Okay. You can listen carefully here. So what I mean to say, if you want to make A2 is equal to 0, if you want to make A2 is equal to 0, A2 is looking to be the reflection from port 2, provided if you are looking it from the port 1. So in order to make the reflection should be 0, your impedance has to be matched. So the impedance get matches out provided you have to connect a physical load of 50 ohms. So in order to measure the value of S1, this particular transmission line has to be terminated with 50 ohms at the second port.
So
Yeah.
how are you saying that A2 it will be a reflection from port 1? Like by seeing the direction, you're
No,
saying
I
that
was
it's
looking it from the port 1, right? When you look from the port 1, how A2 is looks to be there?
uh,
See here, I have not applied any voltage on the second port, right? Okay.
yes, sir.
You have applied only on the voltage on the first port.
Yes.
So when you apply some voltage on the first port and it reaches the load, okay.
Hmm.
If it reaches the load, do you think your value of A2 will be 0? There is no voltage applied at the first port. You
Yes,
can see
sir.
here, I have applied voltage here and I have not applied anything here. So automatically some voltage will go here, right?
Correct. Yes.
Now, in order not to have any reflected voltage from port 2, which means that when you give some input here, I don't want to have any reflection from port 1. So that's how the definition of S11 lies, right? B1 by A1 provided your A2 has to be equal to 0.
Okay. Okay.
Agree?
Yes, sir.
If I don't want to have any reflected wave again back to port 1, I need to terminate with a 50 ohm load. Agree? Then only I don't have any reflection. So whatever I will send here, everything will be absorbed by the load.
Okay. Okay. Okay,
Agree?
sir.
Now you understood?
Yes. Yes, sir.
Yeah. So in order to measure S11, you have to terminate the second port with a 50 ohms impedance. And your port 1 impedance is anyhow 50 ohms. And the element, whatever the network you are having is also 50 ohms. So this is your A1 and this is your B1. So can you tell me what is the B1 by A1 represents in that case? That is the reflection coefficient at port 1. So if you calculate the reflection coefficient at port 1, you find out what is the effective input impedance here. So you can see here the effective input impedance, if you are finding it out, it will be the sum of this 50 ohms and this 50 ohms. When you look from this particular side, what is the total effective impedance? It will be equal to 100 ohms. So my value of Zin equal to 50 ohms and my Z naught equal to 50 ohms. So what is the reflection coefficient equation we have given? If you see here, this effectively work as a load impedance when you look at from the port 1. So this ZL minus 50 ohms divided by ZL plus 50. So the reflection coefficient equation is what? ZL minus Z0 by ZL plus Z0. Actually, when you look at from the port 1, the effective load impedance is same as your Zin. And you already got Zin equal to 100 ohms because these two are connected in series. So can you tell me what is the value you are getting? So this equal to 100 minus 50 divided by 100 plus 50. So you are going to get S11 is equal to 50 divided by 150. So that is equal to 1 by 3. So do you have any questions here? Yeah. So can you do the next case for, so the value of S11 is equal to 1 by 3. So what you can do the next case, S21 you try to do. So even if you are measuring S21, yeah, 2 by 3. So what is the formula you have used?
Sir, transmission and reflection sum equals to 1, sir.
Yeah, transmission and reflection.
Yes, sir.
No, it's the other way, right? So what is the formula? Tell me.
Gamma T equal to 1 plus gamma V.
Then?
And gamma,
Hmm.
then this shall be 1 by 3 plus 1.
Hmm.
It will be 5 by 3, sir. Yeah.
No, it is wrong. So that kind of things and all will not work here. Okay.
Okay.
Okay, we'll try our method. See.
Yes.
Yeah. So even when you want to find out your S21, that will be equal to B2 by A1 provided A2 will be 0. Again, the same thing I will apply here. I don't want to change anything. In order to make your A2 will be 0, you have to connect a physical load impedance of 50 ohms. Okay. In this case, what is the case here? This is your A1 and this is your B1. And of course, what will be the value of A2 here? It is equal to 0. And there should be something which is transmitted into the second port. So I don't know the value of that. Agree? This diagram is clear for everybody. I have applied some voltage here. So there will be some reflection. And since the impedance is matched, there is nothing reflected from port 2. And of course, something will be getting transmitted to the second port. So let me call it as port 1. And this is my port 2. The characteristic impedance is 50 ohms here. Okay, that is same. What will happen when you apply any voltage here, since you have terminated in series, there will be some current flow here. Okay, and let me call V1 is the effective voltage at port 1 and V2 is the effective voltage at port 2. Okay, so when I say the effective voltage at port 1, I already told you in the first class. The net voltage on a transmission line is the sum of the forward and reflected. So can you tell me what is the effective voltage of V1 here? You can tell me what is the effective voltage of V1? Are you there? 100i. Yeah, that is 100i only, that I agree. But what I can say, the effective voltage here is the sum of incident and reflected. That's what I was saying. So I can say V1 is the sum of A1 plus B1. V2 is the sum of A2 plus B2 using our basic equation. Okay. First one, V1 is equal to A1 plus B1 and my V2 is equal to A2 plus B2. In this case, your A2 is 0. Okay, when A2 is 0 means your V2 is basically said to be B2 itself. Now, so how to find the value of V2 here? I can say V2 is equals to, I can use the current division. You can see the KVL application, right? The value of V2 is equal to V1 into 50 ohms divided by total impedance. Everybody agree with me? Whatever the voltage observed at V2 is a voltage division principle. Whatever the voltage you are applied into 50 ohms divided by the total impedance. Okay, what is the condition you are getting? That is equal to V1 divided by 2. And you already know the values, right? B2 is nothing but B2. So I can say B2 is equal to 1 by 2 times V1 means A1 plus B1. Okay, so now what I will do, I will divide both the equation with A1. This one can set to be S21 is equal to 1 by 2 times. If you compute this factor, what you are going to get 1 plus B1 by A1. Okay, so what is the value you are getting? S21 is equal to 1 by 2 into 1 plus. So B1 by A1 is the reflection at port 1. If you see here, B1 by A1, the reflection at port 1, that is nothing but S11. So we have already found out what is the reflection coefficient, right? So just now before, you already get the value equal to 1 by A. So if you substitute that, what is the value you are going to get? 2 by 3. Okay. So your S11 is equal to, so two parameters you will be able to define. S11 is equal to 1 by 3 and S21 is equal to 2 by 3. Is it clear what I'm saying? Do you have any questions to ask? You can ask me now only.
This is
Yeah.
like complicated. Means like
Mm.
yeah, means
Complicated
lengthy.
means
Means like
lengthy.
means like
Mm.
we will like apply 1 0, then again we'll find KVL.
Nah, that's what see, it's not confusing. EMT is all about application of all your subjects.
Yes,
See,
sir.
just now, even in the previous discussion also, when I was discussing impedance matching, I have gone to your analog circuits to discuss about common emitter, common base amplifier. Okay. And
Yes,
now I was going to discuss about your network theory.
yes, sir.
Okay. So, and especially mathematics is a basic subject. So, EMT is a part of mix of everything, you know. That is
Yes,
the
sir. Yes.
beauty of the electromagnetic theory. Okay. It's
Yeah.
not like confusing. Once basics will be there, then you will be able to understand everything. So I have not done anything. I was mixing up my electromagnetic theory with your network theory. So
Yes,
both
sir. Means
together
like
I was mixing. Yeah.
here you divided by A1 so that you could
Yeah.
get like B1 by A1 because we had found B1 by A1.
Exactly. That's it. Because even when I was approaching, you see here, first of all, I was after S11, what you think generally, I may discuss about S12,
Yes, sir.
isn't it? But I have not discussed that. Why? Because S11 and S21 can be simultaneously founded out when you put A2 is equal to 0.
Okay, sir.
Okay, so if I do S11 and go to S12 and come back to S21, it will be more confusing.
Okay, sir.
Yeah, so when you put A2 is equal to 0, simultaneously we'll be able to define what is this parameters under. Okay,
Oh,
at this point it looks to be confusing, but when you see for the second one, you try to go in a sequence, you will be able to do the answer. Okay,
second one will be
yeah, second one. This is your second problem.
is
Sir?
the same type. Only thing is like that 50 ohm series will be in parallel in the
Correct,
same.
correct.
Okay.
Yes. So you have to apply the same concepts and try to find what is the answer. And before this, right now, let me conclude this.
Yes, sir.
So for the first one, you are getting S11 is equal to 1 by 3 and S21 is equal to 2 by 3, right? and the network is looks to be symmetrical, right? Or you can say, sorry, not symmetrical, it's a reciprocal, which means that even if you look at the network from port 1 and even if you look at the network from port 2, is it appear same or not? The way however you look like, the network is looks to be the same. Even if you look into port 1 or look into port 2, the appearance is same, which means that as per your network theory is concerned, it is said to be reciprocal. Okay, so whenever it is reciprocal, the reflection at port 1 is same as your port 2, of course, because it is symmetrical also. Reciprocal means the transmission from port 1 to 2 is same as port 2 to 1, because this series element will be common even when you apply input 1 here or input 2 here. So the network is reciprocal means the transmission from port 2 to 1 is same as port 1 to 2. And since whatever the impedance you are present on the port 1 is same as the impedance at port 2. So what happens to the reflection here and reflection here? So because the reflection is basically ZL minus Z0 by ZL plus Z0. So the effective load impedance here and effective load impedance here is same. And Z0 is anyhow both are 50 ohms. So I can say reflection coefficient at input side and output side, that also same because of the symmetry. So I can say your S11 is equal to S22 and the transmission is also remains same because of the reciprocal. So I will give all those properties later. What is the characteristics of the S matrix and all. So just by observation, I was telling that S11 is equal to S22 and S21 is equal to S12. Yeah.
Can we use like transmission coefficient is equal to 1 plus reflection coefficient for S21?
For S21, no, you cannot use. In this case, is it satisfying?
Means it gives the same answer, sir.
No, it's not satisfying, right? When you put 4 by 3, you are going to get.
Okay, sir. Okay, sir.
Yeah, correct. It's not that. Okay. Next thing. So if you put it in S matrix, so what is the final answer? S11 and S22 both are same, which means that all your diagonal elements is 1 by 3. And when you take the another diagonal pair, it will be 2 by 3. Okay, so this is your original S matrix right now. So can you do the next one now? Even this network, if you see here, this is also looks to be symmetrical from both the ends. So calculate S11, it is same as your S22. And even if you apply the input from here, whatever the response you get it in the second port, the same thing will happen when you give the input at port 2. So the network is also reciprocal. To keep it in simple, all your passive elements are said to be reciprocal and symmetrical. That's what you studied in your networks, right? So when you have a resistor, inductor, and capacitor, all those circuit elements is said to be reciprocal. So first find the S matrix for the second thing. Okay, so do it for the second one. So this is your two-port network, and this is your 50 ohms, and this is your 50 ohms, and here the port 2 to also you are having 50 ohms. Again, the same condition. If you want to find out S11, that is equal to B1 by A1, provided A2 is equal to 0. So which means what is the condition? In order not to have any reflection, the second port should be terminated with a 50 ohms. So physically, if you see here, this is one resistor here, and these are another resistor. So can you tell me what is the effective input impedance here? Zin? Good. 250 ohms in parallel. So you are going to get 25 ohms. So once if you know the effective input impedance here, what is the reflection coefficient? Using the same formula. S11 is equals to B1 by A1. Is same as the effective load impedance minus Z0 by effective load impedance plus Z0. So your S11 is going to become 25 minus 50 by 25 plus 50. Okay, so what is the value you are going to get? Minus 1 by 3. Agree? Yeah. Now you can do the value of S21 right now. S21. So your S11 is equal to minus 1 by 3. So do the same thing for S21. Even when you are calculating S21, it is the ratio of B2 by A1 provided A2 is equal to 0. So for that also, we have to terminate the load impedance with a 50 ohms. So we'll have an incident wave here and reflected wave. And in this case, your A2 will be 0 and you are having only the value of B2. Okay, this is your voltage at port 1 and this is your voltage at port 2. It's a basic simple network. You can find out that. Can you tell me how to do? So if I assume that there is some current here, so what is the voltage observed at second port? The voltage observed at this particular point can be how much? V1. Is it V1? You are missing one important point here. What is that? It's not your actual network, it's a transmission line.
Okay.
Yeah. So when it is a transmission line, the voltage at this point may not be voltage at this point.
Okay.
Is it clear? Yeah.
Yes, sir.
So that point you should not miss. Yeah. You can do that. You can try and tell me what is the answer you are getting. See here, first thing I can say that what is the effective input impedance you are getting here? Zin?
25, sir.
Yeah. So what is the first equation you are going to have? V1 is equal to I into 25. Agree?
Yes, sir.
So this is your first equation. So similarly, can you find out V2?
I by 2 into 25.
Yeah. So first of all, when you see V2, what will be the current flowing through this particular branch? So whenever some current is going to enter here, since both the resistance are same, it is going to distribute equally.
Yes, sir.
Yeah. So in this case, here it will be I by 2 and here also it will be I by 2. Okay. Agree with my point?
Yes, sir.
Yeah. Then you can do that now.
So again, we are getting same 25.
Yeah, yeah, correct. It is 25 only in this case. Because as long as you are assuming that, here also see, you are assuming that current remains same, right?
Yeah.
You have assumed that there is no losses. So in that case, V2 is equal to V1. Correct. What you said was correct.
Okay.
Because you are assuming that it is a lossless and current is also not dropping. Yeah.
Okay.
Yeah. Now you can do that. So when your V2 is equal to V1, what is the V2 total value?
B2.
Yeah. And what about V1?
A1 plus B1.
Yeah. Now you divide both the equations with A1 in order to have S21.
Okay.
Okay. Then straight away we'll get this is equal to S21. So in this case, whatever you said was correct. 1 plus gamma you are going to get. So your S21 is equal to 1 plus B1 by A1. So this is equal to 1 plus S11 straight away. B1 by A1 is equal to S11. So what is the value you are going to get? S21 is equal to 1. S11 equal to minus 1 by 3. So you are going to get 2 by 3 here. So can you tell any questions here?
No, sir. So we can directly like do like voltage, input voltage. Yes, I
Ah,
got it.
yeah. So then finally, what is the S matrix you are going to get? You can formulate like minus 1 by 3, 2 by 3, 2 by 3, and minus 1 by. Okay. This is your final S matrix. Okay. So first I will give the properties of the S parameters. Okay. So this anyhow you are going to study in microwave. So just I will tell a simple points. Oh, what is that? So when you say anything, if it is a reciprocal network, your original S matrix has to be equal to the transpose of that matrix. Will you agree with me? Just now, even in the problem also you have seen S12 is equal to S21, which means that even if you interchange the diagonal elements, your transpose matrix is going to become same. So you can, suppose if the S matrix is 3 by 3 matrix, so instead of verifying all the diagonal elements, you just take what is the transpose of the matrix. If the transpose of the matrix is same as your original matrix, then the two-port network is said to be reciprocal. And one more important point, when you say any particular network is lossless, this is very important condition. I don't want to tell you the proof, you just remember the original matrix into the conjugate matrix has to be equal to I. So you are going to study in the microwave, but anyhow, till now they haven't asked any questions, but it is very important to remember. So when any network is said to be lossless, you multiply the original matrix with the complex conjugate. That matrix is equal to unit matrix. Then you can say the network is said to be lossless. Lossless. Okay, just I will give an example. You can understand it better. So you see this matrix. Is it reciprocal or not?
Yes, sir.
Yeah. And you verify is it what you can say lossless or not?
Yes, reciprocal then
Yeah.
lossless.
Reciprocal means it need not be lossless always.
Oh, okay, okay.
Okay. I will give an example for that also. See, S transpose is equal to S. So basically reciprocal condition is satisfied. What is the condition I told you lossless means your S into a complex conjugate has to be equal to I. Suppose if
Oh,
your
okay.
real matrix is, if your S matrix is real, see the S matrix itself is a unit matrix. Agree?
Yes, sir.
So in this case, what you are going to get 1001, and here also you are going to get 1001. So what value you are going to get? The multiplication also equal to a unit matrix. Okay. In this case, the network is said to be reciprocal and lossless, both. I'll give you another example. Just see the previous example. What is the values you are getting? This one. Is it reciprocal or not? Have a look on this.
Yes, sir.
Verify whether it is lossless or lossy.
Oh, okay.
So your S matrix will be minus 1 by 3, 2 by 3, 2 by 3 into minus 1 by 3. So if the S matrix is real, even your complex conjugate is also S only, right? But when you will have a complex S matrix was when you go for the H plane T, E plane T, magic T junctions and all, especially in microwaves, there will be a phase shift when the wave is entering from port 1 to port 2 and so on. So that case you can expect a phase shift. So your S matrix is going to become a complex matrix. As long as these conditions are like this, you need not to worry. If all the S matrix are real, the conjugate is also same as that. So what will happen right now? S into S conjugate. So verify you are getting the unit matrix or not.
No, sir.
Yeah. So you can verify if you want. So you can see here the first element will be 1 by 9 plus 4 by 9. So this itself is not equal to 1. So you need not to verify. So this is not a unit matrix. So reciprocal nature is different and lossless nature is different. See, lossless nature coming into the picture provided if the length of the network, based upon the length of the network, it is going to matter. Suppose if you have a directional coupler or if you have a H plane T or E plane T, where the length is quite high, you can expect that there is a phase shift. And because of the phase shift, when it is moving from one port to the other port, you would have been seen in the circulators. So if the length of the network is much higher compared to the wavelength, the moment whatever you are entering here, if it is trying to reach the second port, there will be some losses in this network. That time your matrix is basically going to be the matrix is going to get a complex matrix because of this additional phase shift. The simple example was for all most complex S matrix, the network is said to be lossy. Okay. So any questions you have? Yeah. So then we'll discuss the last topic, that is the Smith chart in the transmission lines. Okay. That is it's a theoretical topic only. But from the past 2 years, I don't know the reason being why they're giving more stress on the Smith chart. So have you seen the Smith chart? Really? Have you done an experiment on any Smith chart and all in your graduation?
No, sir.
No, you haven't seen Smith chart.
We hardly understood EMT anything.
No. You would have been seen the Smith chart, right? At least.
I'm not able to recall, sir.
Oh, how many years over?
Many years.
Many years. Okay. What about others? Yeah, it was there, but not remembered, right? Basically, that is a condition, right? Even the faculty, whoever is teaching, they will not be aware of what is that Smith chart and how it is basically used. The persons, whoever is really working on that, they only will be able to understand what is the actual applications of the Smith chart. So the first thing was the Smith chart is basically the graph between your real part of the reflection coefficient and imaginary part of reflection coefficient. Okay. The first thing is this one. So when you see the Smith chart, the real axis is the real part of reflection coefficient and imaginary axis is the imaginary part of reflection coefficient. So we already defined the reflection coefficient is a complex quantity, right? So you will have a real part plus imaginary part. Okay, the real part I have defined by this one and the imaginary part of reflection coefficient is this one. So what will happen when you have a different type of loads connected to different transmission lines? You will have a different family of the circles. So to understand that, let me give an approach how the Smith chart has been designed. Okay, first thing, if you have a transmission line and which is terminated with a particular load. In order to proceed any problem with the Smith chart, first thing you have to do is the normalized load impedance. So what do you mean by normalized load impedance was, you just divide the load impedance with the characteristic impedance. So this process is called normalization. Now, by having a look on this equation, can you tell me the normalized load impedance is a real number or a complex number? Tell me quickly. Is your normalized load impedance is a real number or a complex number? Complex. Yeah. You don't know what kind of load you are going to connect to the transmission line, right? So if you are going to connect a complex load, the ratio is also going to become a complex number. So if I generalize it, the normalized load impedance is of the complex quantity, which is called R plus Jx. Okay, where I can call R is my real part of normalized value, and X is basically said to be the imaginary part of normalized value. Having said that, we know what is a reflection coefficient, right? The reflection coefficient is equal to ZL minus Z0 by ZL plus Z0. And you can divide this, right? Both numerator and denominator, you divide with Z0. So what you are going to get, ZL by Z0 minus 1 by ZL by Z0 plus 1. Okay, now what will happen? This reflection coefficient is also complex quantity, and this is also going to be a complex quantity. So what is this complex quantity I have given? Gamma R plus J times gamma I is equal to, so ZL by Z0, you are going to get it as R plus Jx, just now we have seen, minus 1 by R plus Jx plus 1. Okay, this is your reflection coefficient. I was able to express in terms of the normalized load impedance. Okay, next thing was you just do the mathematical manipulation, something like you rationalize this fraction and you are going to get some complex number, right? After that, you just equate the real part and you equate the imaginary part. You will get the two equations. So those equations I was straight away writing it here. Okay. And if you want anyhow, I can attach the derivation part in this document. You can go through that. It will be helpful. But the approach is this. When you rationalize this particular part, you will get a real part and some imaginary part. Just equate the real part, you will get one equation, and equate the imaginary part, you are going to get another equation. Okay, after equating the real parts, straight away I was writing, you are going to get this equation. Okay, when you equate the real parts, you are going to get the value in terms of R only. Similarly, when you equate the imaginary parts, you are going to get another equation in terms of the X, reactance value. Okay, so if you see here, as I said, the Smith chart is the graph between the real axis gamma R and gamma I. So gamma R is nothing but your x-axis and gamma I is your y-axis. If you keep on varying the value of R, what is this equation? So this equation is in the form of x minus a whole square plus y minus b whole square is equal to R square. So the first equation represents the family of the circles if you keep on varying the value of R. Similarly, the second one is also represents the family of circles when the value of x is changing. So do you remember, first of all, what is R and X represents? R and X is basically the normalized load impedance. If you want to have a different value of R and X, you need to have a different load. So ultimately, what is the point? If you have a transmission line, if the load changes continuously, your value of R and X will continuously change. So for each value of R, you are going to get one circle. For each value of X, you are going to get another family of circles. So the intersection of all these family of circles is basically going to form a Smith chart. So any questions here? If you want, you can ask right now before going to the next discussion. So have you understood? The Smith chart is the combination of the family of circles. So whenever your load connected to the transmission line changes, you will get one equation of the circle. So suppose if I connect a short circuit load, your R will be 0. When your R will be 0, you will get certain equation here. That we will discuss in the next section. So each load is going to have a special impact on the Smith chart. Is it clear? Yeah. So first I will discuss about one family of circles. So after equating the real part, so you are going to get one family of circles that I can call it as a constant R circle. Or you can say constant resistance circles. So let me write the equation again. So this is gamma R minus R by R plus 1 whole square plus gamma I square is equal to 1 by R plus 1 whole square. So can you tell me, by comparing this equation with a circle equation, so where the centers are located? You can turn on your microphone quickly. So it's already 11:10. So you can switch on the microphone and tell me where the centers are located
Yes,
by
sir.
comparing. Yeah.
R by R plus 1 and 0.
What about the radius of the circle?
1 by R plus 1.
Yeah. Thank you. Now we'll keep on varying the value of R and let us find out what happens to the Smith chart right now. So for that, so let me take, this is my gamma I axis, and this is my gamma R axis. Okay, as a first case, I can consider R is equal to 0. So can you tell me what is R equal to 0? The nature of the load means? What is the nature of the load when I say short circuit, correct? So because when you have a short circuit, ZL equal to 0, so your ZL by Z0 is also going to become 0. So when I say R is equal to 0, the nature of the load can be short circuit. Do you think is that only one case? Is there any other case possible?
Purely imaginary.
Good. If your load impedance is purely imaginary or purely inductive, so even in that case also, your R will be 0. Okay. So when I say R is equal to 0, it can be a short circuit load or it can be a pure imaginary load. Okay. So where the center is located, when you substitute here, the center is located at 0, 0, and the radius is located, calculated as 1, right? Subjected to R is equal to 0. So where the center is located, this is your center of the circle, and it is located at 0, 0, and having a radius of 1. So let me assume this is my 1 meter, and you can draw a circle like this. Okay, this is corresponding to R is equals to 0. Okay. So let us consider the second case. So when R value is equal to 1. So can you tell me when R value is going to become 1? Quickly. When you are going to get the normalized resistance is equal to 1.
Match case, sir. ZL equal to Z.
Exactly, you have to remember. So when ZL equal to Z0, you are going to get the ratio is 1. which means your r is equal to 1 and x is equal to 0. So when r is equal to 1, so where is the center? So 1 by 2 comma 0 and your radius will be 1 by 2. So 1 by 2 comma 0 means somewhere here. So this is my 1 by 2 comma 0 and your radius will be exactly half this much. So your circle is going to become like this. So this is my circle, r is equals to 1. Okay, let me take some intermediate value and find out. So when I take r is equal to 1 by 2, so where is the center located? So please cross check. You are going to get 1 by 3 comma 0 and the radius will be 2 by 3. Correct me if I am wrong. So you can see here the second one is having a radius of 0.5 and this is having a radius of 0.66, which means that so this is your r equal to 1 circle having a radius of 0.5. So if I say radius is equal to 0.66 means somewhere here. So this is your what you can say 1 by 3 comma 0. So r is equal to 1 by 2 circle may be something like this, slightly bigger than the second one. So this I can call it as r is equal to 1 by 2. Any questions here till now? Am I correct? Whatever I have drawn there. Shall I go ahead?
But they will always stay inside that r equals to 0 circle.
Yeah, correct only, no? Because r equal to 0 circle is having radius 1.
Okay, sir. Yes.
Okay, no? So 1 by 2 means it has to stay inside only. There is no other point. It cannot exceed, right? Because the radius is small. Okay, next case, let us consider r is equal to 2. So your center is going to located at 2 by 3 comma 0 and the radius is going to located at 1 by 3. So 1 by 3 means 0.33. So which will be very smaller, you can say. So this circle is located at r is equal to 2. Okay, let me do it r is equal to infinity. So can you tell me what is the nature of the load? R equal to infinity means quickly.
Open circuit, sir.
Yeah, it is an open circuit. So center is located at, so you are going to get infinity by infinity. So you take r common. So you are going to get 1 comma 0 and radius is equal to 0. 1 by infinity is 0. So which is nothing but 1 because this is 0 0 and the radius is 1. So 1 comma 0 is this point where your r is going to be equal to infinite. Okay. So any questions here right now? First, do you have any questions to be discussed? So these conclusions are very important. You listen to the first conclusion. So what is the first conclusion? Out of all the constant resistance circles, the biggest circle is R is equal to 0, corresponding to short circuit load. And the smallest circle is corresponding to R equal to infinity, open circuit load. Agree? Agree?
Yes, sir. Yes.
Yeah. So when you see all these cases, the biggest circle is R is equal to where the nature of the load is short circuit, and the smallest circle is R equal to infinity where it is a open. There is one more common point here. The center of all these circles are located on the real axis. You can see here, whatever the circle you take, the second coordinate is always 0, which means that the centers are located on the real axis. That is the second point. The third point, whatever the circle if you take, all those are having a common point at 1, 0. In this equation, you substitute gamma r is equal to 1, gamma I is equal to 0. So irrespective of the value of r, this equation is going to satisfy. Which means that all the circles should pass through 1, 0. So they have a common tangent at 1, 0. Agree?
Yes, sir.
Yeah. Next last point, very, very important point. See, actually, the reason being why I was telling all these derivations, I can straight away tell you the conclusion. It's something like, there is no starting and there is no ending. Just I was telling some simple words to you. So it should not be like that. So that is the reason why I was telling you the complete flow. Okay, next last point is, you can see here this, let me call it as a first quadrant, second quadrant, third quadrant, and fourth quadrant. When R lies between 0 and 1, so actually R basically represents the resistive nature of the load. If the resistive nature of the load is closer to 0, which means that I can call it as a less resistive load. Okay. R basically represents what is the total resistive portion of the load. If the resistive part of the load is closer to 0, I can call it as a less resistive load. So how many quadrants that circle is? As an example, you can consider R is equal to 1 by 2. So if you take R is equal to 1 by 2, you can see here, this is your R is equal to 1 by 2. It is going to cover all the quadrants. So when the nature of the load is purely resistive, and if it is very less value, so the circle on the Smith chart corresponding to all the quadrants, it is going to cover all the quadrants. 1, 2, 3, and 4. So can you tell me, when the value of R is greater than 1, I can call it as a high resistive load. What all the quadrants the circle will be confined to?
1 and 4.
Yeah. So which means that you can take R is equal to 2. So when you take R is equal to 2, it is confined only to the first quadrant and the fourth quadrant. So these are the conclusions. Okay, you need not to worry. I was going to upload the PDF, right? So there you will get all these conclusions and that. Okay, right now you don't have the time to note it down. I will put all the conclusions while uploading in the drive. Okay. Okay, this is all about constant resistance circles. Okay, next we will move on to the constant reactance circles. So when you see the constant reactance circle, let us have a look on that family of circles what we got. So here the centers are located at 1, 1 by x, and the radius is given by 1 by x. Okay, I can draw the same thing. This is your gamma r axis, and this is your gamma I axis. Okay, so first thing, let me start with x is equal to 0. So tell me, what is the nature of the load?
Resistive.
It is a resistive load, or it can be
Purely real.
or it can purely resistive load, or it can be a short circuit load. Correct. Okay, so when your value of ZL is equal to 0, you are going to get R is equal to 0 and X is equal to 0. So when I say X is equal to 0, it can be a short circuit load,
Okay.
or it can be a purely resistive load. So two combinations will be there. Yeah. So tell me, where is the center located? So the center is located at 1, infinity, and the radius is going to be infinity. Okay. This is a very, very bigger circle. I cannot represent in a Smith chart, right?
Yes, sir.
Yeah, so in that case, I can assume that x is equal to 0 is a circle where the radius is the entire real axis. So to make sure that I can represent by x is equal to 0 as the entire radius of the real axis. Just for the representation, because it is a very big circle, I will not be able to represent in the diagram. Okay, so for considering that, I was taking the entire real axis as the x is equal to 0. Okay, next let's start with x equal to plus 1. So when I take x is equal to plus 1, your center is going to located at 1 comma 1 and the radius will be 1. Okay, so this point is 1 comma 0. So 1 comma will be somewhere here. Agree? Now when you take this one as a radius and you try to, and the circle is also going to pass through 1 comma 0. Even in this equation, you can see here, all the circles has to pass through 1 comma 0. If you put gamma r is equal to 1, gamma I is equal to 0, this both the sides, the equation is going to satisfy. So the circle has to go through this point and should have a radius of 1. So how that circle is looks like? So I can represent it like this. And it is going to make a complete rotation. I don't want to bother about that, because my particular point of interest is what all the portion where it is getting intersected with R circles also. So when you go outside, it doesn't matter. You can leave that part. So the circle is going to like this and again reaching back the same. Okay. So this is going to call it as x is equal to plus 1. So can you tell me what about x is equal to minus 1? Is x is equal to minus 1, is it possible for a different loads? Can the value of x can be negative? Yes or no? Yeah. What is the possibility when the x value can be negative and when it can be positive?
A capacitive negative and inductive positive.
Correct. So when I was talking about resistance, it is purely a positive number. You don't have a negative resistance. So I don't consider any negative resistance there. So when you talk about reactance, reactance is positive for inductive load and it can be negative for capacitive. So when you have a capacitive load, you may have something like x equal to minus 1. So there, the center will be located at 1 comma 1 and the radius will be anyhow. Obviously, you are going to take the magnitude for that. So when you take the magnitude, that is also equal to 1. Sorry, center is located at 1 comma minus 1. So 1 comma minus 1 is exactly at the downside. This is your 1 comma minus 1. And radius is 1. So since the circle has to pass through this and this is your radius, so your circle is something like this and going to full portion. So this is equal to x is equal to minus 1. Okay. Similarly, or in other words, what I can say, if x is equal to plus 1 is this, the mirror image of this one will be x equal to minus 1. Okay. Similarly, you quickly do it for x is equal to plus half. So when I take x is equal to plus half, your center is going to located at 1 comma 2 and the radius is equal to 2. So just cross check whether I was doing correct or not. This will be something like this, x is equal to plus half, because it is a bigger circle because the radius is 2. So 1 comma is your center. So x is equal to 1 is having a radius of 1, and in order to have a more radius, the circle may cover like this and it can make a rotation. And similarly, you can see the mirror image of that is going to be x equal to minus half. Next thing, when you take x is equal to plus 2, the center is located at 1 comma 1 by 2 and the radius is equal to 1 by 2. So radius half means this circle is having a radius of 1. So 1 by 2 means maybe somewhere here. 1 by 2 comma 1. So your circle is going to cover a small portion. So this equal to x equal to 2. And the mirror image of that one will be x is equal to minus 2. So on the last one, when I say x is equal to infinity, so tell me what is the nature of the load? What is the nature of the load? X is equal to infinity. Okay, correct. So when it is open circuit, what should be the condition? Your center is located at 1 comma 0 and the radius is equal to 0. Okay, so wherever you are got your this point as a r equal to infinity, the same point your x is also going to be infinity. So here you are getting r is equal to infinity. Okay, so any clarification you need here, I will be able to do.
Sir, x equal to infinity, why it is open circuit?
X equal to infinity means when you will
Okay.
get x
ZL
equal to
will be
infinity,
okay.
ZL will be infinity. So in this
Yeah.
case, r and x both will be infinity, you can assume.
Yes, sir.
Yeah. So the first conclusion you can see here, what is the first conclusion here was the centers of all these x circles is located parallel to the imaginary axis. If you can see here 1 2 1 comma 1 1 by 2 comma 1 1 comma 0. So the centers of all the reactance circles is parallel to the imaginary axis at 1 meter distance. You can see here the real part is always equal to 1 in all the cases. So the first conclusion is the centers of the reactance circles are parallel to the imaginary axis at 1 meter distance. And reply, which is the bigger circle here out of all this reactance circle?
X equal to 0.
Ah, so same as that. R equal to 0 is the bigger circle. Here also x is equal to 0 is the bigger circle corresponding to open circuit load. Sorry, short circuit load. And the smallest circle is x equal to infinity corresponding to open circuit load. Okay, and the next third point, even these family of circles are also passing through 1 comma 0. So if you see here, either whatever the circle you take, all will pass through 1 comma 0. So they have a common tangent at 1 comma 0. Next point, it's a very important point you have to assume. So if the value of x lies between 0 and 1, so what is the nature of the load, you can say? X is positive. X is positive means you can say it is an inductive load. And since it is closer to 0, I can say the nature of the load is less inductive. So you can take this as a first quadrant, and this is a second quadrant, and third quadrant, and fourth quadrant. So when the nature of the load is less inductive, example, x is equal to plus 1 by 2. How many quadrants is covering? Tell me quickly.
2 quadrants, sir.
Yeah, first and second. Yeah, that means when you are on the upper half of the Smith chart, your nature of the load is inductive.
Yes, sir.
Yeah. Similarly, the next you can see here when x greater than 1, what is the condition? If it is highly inductive, if x is much greater than 1, example you can take x is equal to 2. So you can confine only up to the first quadrant.
Yes, sir.
Yeah. So the point is very clear. When you move on the upper half of the Smith chart, this is nature is said to be inductive. And when you see the less inductive, it will cover the first and second quadrant. When you see the highly inductive, it will cover the first quadrant. So similarly, you can calculate the third case. if X value is lies between -1 and 0. So in this case, X is negative, so it is capacitive. And it is a small negative number, you can say it's a less capacitance. Okay, since it is close to 0, you can say it's a less negative, which means that less capacitive. So an example you can consider is X equal to -half. So tell me what all the quadrants it is covering?
Third and fourth, sir.
Yeah, third and fourth. And the next thing, if X value is more negative.
Only fourth quadrant.
Yeah, if X value is more negative, means it is going to cover only the fourth quadrant. So, or you can say the nature of the load is highly capacitive. So that is what the full conclusion about the Smith chart. Okay, so this is how your Smith chart looks like, right? Whoever has seen. Okay, isn't it? The Smith chart is going to look like that or not? So whatever I have discussed now. So the Smith chart is going to basically the intersection of your R circles and X circles. So if you see the R circles, this is R equal to 0. This is going to become R is equal to 1 if I summarize all together. And this is going to become R is equal to half. And your R is equal to 2 is here. And this is your R equal to infinity. Similarly, the entire real I told you this is X is equal to 0. X is equal to 1 means it will be like this. And -1 will be the mirror image. Similarly, X is equal to plus half is this. And -half is the mirror image. Same thing. X is equal to plus is here. And -2 is here. Okay. First of all, let us try to understand. You will have a first case. Okay. I had my ZL value is equal to 0. Everybody has to remember every particular load on a transmission line is corresponds to one particular point on the Smith chart. One load corresponding to one point on the Smith chart. So the first thing is how to find out that particular point is very tricky here. So once if you know that the load is short circuited, see that this is your characteristic impedance and this is your ZL. If ZL is equal to 0, can you tell me the normalized load impedance? That is equal to R plus JX is equal to 0 and R is equal to 0 and X is equal to 0. So when I say that, if you want to represent a short circuit load, it is the intersection of R equal to 0 circle and X is equal to 0 circle. So where is the point located here right now? So this is your R is equal to 0 point, right? R equal to 0 circle and X equal to 0 is the entire real axis. So both are getting intersect this particular point. Okay, I can call this as a short circuit load. Agree? So have you understood to do that? So when you know a particular value of load, you do the normalization, then you will get a particular value of R and X. So once if you see the intersection of R circle and X circle, that is the point which is corresponding to that nature of the load. Any questions you have here? Are you there?
Yes, sir.
Yeah. So I thought everybody is silent. I thought everybody is sleeping.
No, sir.
Yeah. So next thing, ZL equal to infinity. So ZL equal to infinity means it's an open circuit. You can say your R will be infinity and X will be equal to infinity. So where R equal to infinity and X equal to infinity are getting intersected. So I already told you, this is the same point. Sorry, this is the same point where your resistance also infinity and X also infinity. So I can say this point is said to be open circuit load. Okay, next case, third point. So suppose if your load impedance is same as the characteristic impedance. Just tell me where is the point located quickly.
One by 2, 0.
1 by 2. No, no. If the load impedance is same as Z0, what is the value of R and X? ZL by Z0 equal to 1, right? So it is
Yes.
basically R plus JX. Yeah.
Oh, okay.
So which means that R equal to 1 and X is equal to 0. Agree. So where is R equal to 1 here? So you can see here, this is your R is equal to 1. This is your R is equal to 1 circle. I am highlighting it here. You can see here, this is R equal to 1 circle. And X equal to 0 is the real axis. So where both are intersecting here? Exactly at this point, correct? So I can say when I say ZL equal to Z0, it is basically the matched load. So whenever the load is getting matched, that corresponding to the center point of the Smith chart. So generally when you see any transmission line, when you go to the industry level, they will just give you the Smith chart corresponding load. If suppose the nature of the load is coming to the center point of the Smith chart, that is very good. The transmission line is very good, which means that it is said to be the matched load. So when I say matched load, it's exactly corresponding to the center point on the Smith chart. Agree? So this is your short circuit point and this is your open circuit point and the center point is the matched load. Sorry, have you understood how to represent a point in a Smith chart? Yeah. So if you understood thoroughly, let me ask you one question. So what is the nature of the load when you are moving on the upper half of the Smith chart? What is the nature of the load when you move on the upper half of the Smith chart? Inductive. You can clearly see the X value positive. Okay. Similarly, when you move on the bottom half of the Smith chart, you are going to have capacitive, right? Upper half represents the inductive nature, the bottom represents the capacitive. And finally, one more question. Suppose I started from this point on R equal to circle. Okay. I was trying to move to this particular point and I was moving on the outer circle. So I was starting from this point. Again, I was reaching this point on zero circle. How much distance I have covered in a wave? Tell me quickly. This I have covered in terms of the wavelength.
Covering 2 pi.
It's talking about what is the total distance when I move on the outer circle in terms of the wavelength.
360 degree. 1 lambda.
One wavelength, huh?
Yes, sir.
No. That's this question. See, when you are moving from this particular point to this particular point, what happens to impedance? Here you are circuit. By the time you are reach this point, you are getting the open circuit.
Yes, sir.
Agree. So when the impedance inversion takes place in transmission line,
Lambda by 4.
correct. So that means when you travel impedance of lambda by 4, your impedance is going to become inverted. So when you move here on a transmission line, this corresponds to a distance of lambda by 4. Okay. Similarly, I can move from here to here. the impedance got inverted. So it is going to have another lambda by 4. So the total length when you move on the outer circle is equal to lambda by 4 plus lambda by 4. It corresponding to lambda by 2. That's what you have studied in maximum minimum also, right? So your maxima and minima are getting repeated for how much distance?
Lambda by 2, sir.
Yeah. So that's it. I was starting a short circuit load. Again, I was ending at the short circuit load. So where my impedance is same. So the impedance same value you can get when you travel multiples of lambda by 2. That's it, right? So that is what why I was telling this one was, see, at a particular, you are having a transmission line. So at the load end, I had a phase shift of 30 degrees. After traveling a distance of lambda by 4, can you tell me what is the phase shift it is going to take?
Pi, sir.
Pi.
Pi plus 30.
See, basically, each other we need to take no. The lambda by 2 is going to correspond to a phase shift of 360 degrees.
Oh, yes, sir.
But in this case, how much you have to travel? Lambda by 4. So lambda by 4 means you will get an additional phase of 1 degrees. If it is 30 degrees at the load, after traveling lambda by 4, you are going to get 180 plus 30. You understood my?
Oh, we'll directly add, sir. Okay.
Directly, assume that it is based reflection is uniform throughout the line.
Okay. Okay.
Yeah. So what I was telling was the phase is going to get shifted by 180 degrees if you travel for lambda by 4.
Yes, sir.
Yeah. So that is the whole thing about Smith chart, I can say. Okay. Any question? So let's see one theoretical question is there. Just I have written here. So see this question and answer. So the impedance is Z equal to Zx for all values of the x in the range minus infinity to infinity mapped to the Smith chart as. So first thing what I told you, when any problem is given, first calculate the normalized impedance. So this is your ZL value, right? So what is the normalized impedance you are going to get? ZL by Z0? Okay, what you are going to, since you don't have any real part, your R value is going to become 0. And you will get some reactance part. Okay, let me call it as something, J into X by 50. Okay. First of all, what do you mean by R equal to 0 circle right now? You are having R equal to 0 and you will have a value of X which ranges from minus infinity to infinity. Can you tell me? Now, what is the answer? R equal to 0 means the center is located at, you please correct it, it's not 1 comma 0, it is 0 comma 0. Okay. So for R is equal to 0, where the center lies in a Smith chart? Tell me quickly.
0, comma 0.
Yeah, that's what you can see now. I already told you. R equal to 0 is the bigger circle on a Smith chart. Okay. So as per this nature of this load is concerned, it is purely imaginary. Purely imaginary means your R will be equal to 0. So your R equal to 0 circle will be something look like this, having a center of 0 comma 0 and radius of 1. So what will happen when you move on this particular thing? So at this point your X will be 0. At this point X will be infinity. And when you reach here, X is equal to plus half, X is equal to 1 and so on. Okay, so when you are moving on the R equal to 0 circle, your X value is keep on changing or not?
Yes, sir.
So what is the answer then? So in this case, as per the condition, it has met. the normalized load impedance is R equal to 0, which means when you move on this circle, everywhere X value is going to change. So when you are on the upper half, you are positive inductance, bottom portion negative inductance. So that nature actually represents a circle of radius 1 meter. You can see here, and center is located at 0, 0. So clear right now? Do you have anything need to discuss here? Yes or no? Quickly reply. If you have any questions, we can discuss. Okay, then that is the end of the transmission lines, and then we have been left over with the waveguides and antennas. So antenna is going to take one class, not more than that. So next one major chapter is there, waveguides. So we'll continue from the next class. So it's already late right now, 11:45. So if you have any questions, please make a note. So in the next class, we will be able to discuss, or otherwise we can discuss in the group. Okay then, see you. Good night.